Hello, everyone. Welcome to the Easy Power Thursday webinar series. My name is Jim Chastain. I'm your host for today's session. And we have a pretty exciting presentation today that has an international flair. So I'm sure that's part of the interest that people are showing up for. And as we are in the habit, before I introduce the presenter, we'd like to run a couple poll questions and get some feedback from the audience. We would appreciate your participation. There's no obligation or liability. It's strictly just to get a perspective on where the audience stands with respect to this topic. So the first question is, how familiar are you with lightning protection system studies? And again, there's no right or wrong answer. It's strictly your particular interest and perspective in the market. As I mentioned, we were receiving a lot of interest on this topic, and we're excited to have the presentation presented from an international panelist. So it looks like we have a quorum. Here's how folks have weighed in on this. Looks like we have a pretty good distribution of interest, which is good, I think. And then the second question is, how many lightning designs do you perform each year on an average? And I, for one, am real curious to see where people are weighing in on this. All right. Thank you for participating. Here's how folks have opined. Excellent. Well, again, thank you for joining us. And our presenter is Mr. Ian Griffiths, who's with Grey Matters Global in the UK. He's pre-recorded this presentation so he can join us online and answer questions real time. We will have a question and answer session after the video plays, so feel free to use the question control box to share any questions you may have along the way. So if you'll give me just a second, we will allow Mr. Griffiths to introduce himself.
Well, hello and welcome to this webinar hosted by Easy Power. We're going to talk about lightning protection design and some of the tools available which can do some of the heavy lifting for us and save us time in the process. So it's a great honor to share this time with you, and thank you very much for engaging with me on this journey. My name's Ian Griffiths. For those that don't know me, I am the principal consultant at Grey Matters in the UK, where we protect life from the harmful effects of high voltage, and that includes lightning. One caveat before sort of going on, you've probably noticed by now that my accent isn't from around these parts. So I'll tend to be more intimately acquainted with the IEC versions of standards that we talk about. So what's the plan for today? Okay, so we're going to cover what the risks are from lightning. It's not going to be a heavy session with lots of science. This is very much an overview. So if this is the first time that you're touching into lightning protection, then we're going to go easy on you on this one. Then we're going to look at the process, what we can do about the risks that are generated from lightning and the approach that we might take. Then practical steps. This is where we look at the tools and the equipment that we might use to save time, to actually get to the nub of the problem, and then open it up to the floor with a Q&A session where you can pop any questions that those burning questions that you've got stored up. Let's dive in and take a brief look at the main character in this story, in this session, which is lightning. I like to think that because lightning delivers a massive range of frequencies during a stroke or a flash, that it has multiple personalities. So lightning has a massive frequency range, right the way starting from DC right up to hundreds of megahertz. So the other thing is that lightning is an impulse discharge process. Atmospheric scientists have found out is that obviously there's a waveform or a wave shape or a signature, if you will, that each lightning flash has. And many times lightning is thought of as only a high frequency event, which it's certainly true that it is a high frequency event, but it does have lower frequency components to it as well. So let's take a real quick look at some figures about lightning. So on average, there are 4 strokes per flash of lightning, and temperatures reach, during a strike, over 30,000 Kelvin, which according to NASA is roughly about 4 times hotter than the surface of the sun. So pretty hot. The electrical field intensity between the ground and the cloud is height dependent. So for every meter away from the ground, so towards the cloud, you gain 30,000 volts. If you're a fan of Pareto, then 80% of lightning strokes will reach a peak current for the first negative stroke of 20 kA. This is according to the IEC 2010 figures. And 20% will reach up to 60 kA, which is, that's a lot. You know, when temperatures reach 30,000 Kelvin plus, then it's pretty obvious the biggest risk from lightning is going to be lightning as a source of ignition. And if you're one of those guys that processes or manages volatile products like petrol or oil or chemicals for that matter, anything like that, then lightning is a red flag item for sure. On the ground, we see lightning risks as a massive discharge of energy into the ground, and this creates and sets up a ground potential rise that can electrocute and kill. It can also cause system failure through transient voltage problems, or otherwise known as surge. Now, IEC have conveniently categorized the risks into 4 categories. So I'm going to cover those now, very super quick. Loss of life, pretty straightforward. Yeah, okay. Number 1. Number 2 is loss of service. And so this can be if you're manufacturing a product, you know, from a factory, and the lightning prevents you from delivering that and completing that manufacturing process, then there is a loss of service there. Got sort of historical buildings, monuments, museums, that kind of thing, where there's a cultural element. And finally, good old economic loss. Pure and simple. Trouble is, trying to unpick what the economic loss actually is a much more of a challenging task than you might imagine. There's a piece from Liverpool John Moores University by Atherton and Ash in 2006, which suggested that 80% of lightning strike incidents involve a petrol-related item or product. And the NLSAI calculated that in 2008, it cost the US economy $5 billion from lightning-related losses. Now, let's take a step back here. This is back in 2008. We now know through climate change that this could be significantly more in today's context, especially when sort of NASA's researchers have identified that for every 1 degree change in the global surface temperature, there is a correlation to 5 to 6% increase in lightning activity globally. So that £5 billion back in 2008 might actually pale into insignificance in today's and near futures. And finally, lightning accounts for 61% of all incidents in storage and processing activities. And when I say storage, that's bulk liquid storage, the petrochem type, and processing activities. Where there's been an investigation, 61% found that this was due to natural events. So interesting figures. So let's take a real quick look at lightning, the process. We've got this storm cell here, this cloud, and we've got this structure here. what we're seeing is a process inside the storm cell called charge separation, where the negative ions kind of separate from the positive ions, the mix, and they congregate on the underbelly of the cloud. You can get storm cells that have reverse polarity. I'm not going to go there on this piece. We just haven't got time. We're taking the majority cases here where you'd see a negative first stroke, which is this scenario here where you've got the negative ions on the underbelly of the cloud. As this storm cell travels in its path along its way, on its journey, it starts to induce a opposite charge on the surface of the ground. So it's almost like a charged shadow, if you like, underneath the storm cell. And it charges up everything in its path with positive ions of opposite polarity to the what's underneath the storm cell. As the leader starts to drop down towards Earth, then the field intensity actually increases between these two, between this space here. And what we get then is a migration of the positive ions through the attractive force between the two bodies. And we get this into corona and then into saturation around points and corners of buildings and structures. And I'm going to show you a couple of photos, or a photo, and you can see these multiple upward streamers. So this is a precursor to a lightning attachment. And this is taken from Dr. Human's book, All About Lightning, which is a fantastic read. I thoroughly recommend it. I don't think it's in print. I'm not sure that it is. It's really hard to come by, but it's definitely worth the effort to try and find a copy. Anyway, so we're seeing that there are multiple streamers. And when I say we're seeing, it's only been captured on video or camera. We can't see this normally under the naked eye. It just happens too quickly. So this is the first step, is the upward streamers towards the downward traveling leader. Let's just go back one. And the key point to note here is that once it reaches its last step in the leader, it then reaches what I call the point of discrimination, where it starts to then hunt around for things to attach to. And the things to attach to that it's looking for are these upward streamers. Lightning is a competitive event. It's looking for who is sending up the most saturated, bountiful amount of positive ions, and it will lightly attach itself. And in this case, it was the tree that got the bonus, and it attaches. And now all the positive ions that were there previously will track up the plasma, the path that's made in the air molecules, up to the cloud, bounce in and around the cloud, try and balance out. They bounce back down again. They return back down towards Earth. And it's this that we see with the naked eye. It is the return stroke of lightning that is visible. And this is why we say that lightning we see is from the cloud to the ground. But in actual fact, the precursor of a lightning strike is from the other way. It's from ground to cloud. So a couple of things to note there is lightning is a competitive event. And number two is this point of discrimination want you reach the last leader and it starts to sweep around to find what it's going to attach to. So those are the key points I want you guys to take away from that. And we're going to go on to where you start. So if you're new to lightning protection design, there are two main standards to consider, and it kind of depends where you live in the world. So two standards to consider: the IEEE and the IEC. The IEEE covers North America, Canada in gold color, and other countries, as we can see, Japan, some parts of Indonesia, South America and the like. And the IEC is the blue, so everything in blue. And you're wondering, what are the purple countries doing? Well, they're actually applying both standards simultaneously. So interesting. So the IEEE standard is 998, which covers the lightning protection for substations. And in the IEC version, it's 62305. There are a couple of other standards of note. For the States and Canada, you've got the NFPA 780, and also for bulk storage tanks in petrochemical industries and sectors, you've got the API 545, which covers bypass conductors and things like that. We're going to have a look at IEC 62305 now. I don't have a lot on IEEE 998, but like I say, if you're feeling a little overwhelmed, speak to the team at Easy Power, and if you're in the States, or speak to us if you're in Europe for that matter, and we'll endeavour to help you out. So the IEC 62305 consists of 400 odd pages broken up into 4 parts to try and make it a little bit more palatable. The key ones to look at are part 2, the risk assessment and how to install the external protection measures, and part 4 is the internal protection, so the surge protection side of things. So those, the part 1 is really about characterizing lightning and the theory behind it all. So like I say, if you're feeling a little bit overwhelmed, don't worry. David and Easy Power and the team can help out, or if it's in Europe, then we're only too happy to help out as well. So the process, real quick, is you need to, in both standards, you need to define what the LPL is. LPL stands for Lightning Protection Level or Class of Protection. And we do this by risk assessment. Step 2, measures, shielding, what it's going to look like, how, where deployed, that kind of stuff. Once you've done these 2 steps, then you can move on to the design side of things, where then you select the protection method that you're going to use. So I'm going to bounce back into step 1, the most important part of the process initially, to get that LPL. And you consider the frequency of lightning, all the hazards that are there, what the occupancy is. Is it a football stadium that's going to have 70,000 spectators at any one time? You know, the level of panic is going to be huge if there's a lightning strike to that. So that's going to be a high risk issue. Whereas if it's going to be an automated warehouse like Amazon or whatever, there's going to be very little occupancy there. So its threat to life is less. So once we've determined the level of protection required, we then look at the, like I say, the lightning protection measures and the surge protection measures. So we use DenSupport as our software tool to do a lot of the heavy lifting on the risk assessment. And you can use a spreadsheet and do it manually, but to be honest, it's going to take a couple of months to code the spreadsheet. And then if you get an update from the standards, then you're out of date straight away. So that's a risk in itself. But what I like about this particular piece of software is that it gives a graphical representation. So the blue ribbon is tolerable risk, which is tolerable risk for R1 is 10 to the minus 4 or 1 to the minus 5, 100, 1 in 100,000. And we can see that this one is almost off the scale in this case, but we've mitigated with our measures, with our lightning shielding and surge protection, and we've brought it down to almost half of the tolerable level, and which has left us a bit of headroom as well to spare. So that was a good outcome there, which means that we can move on to the design and decide which protection concept we're going to apply to the structure that we're looking at. Now, IEEE uses very similar methods to IEC. You call it fixed angles, we call it angles of protection. You also use empirical curves. We don't tend to use that in the IEC version, but you do use EGM, the electrogeometric modeling, which is equivalent to the rolling sphere. I think the Ericsson method you guys use on the IEEE. We're going to take a look at rolling sphere next. So we're going to take a look at the rolling sphere concept in a little bit more detail. Now, cast your mind back to the slide where we talked about the process of lightning. And if you recall mentioning the point at which the downward leader reaches its last step, and it starts then to, it reaches its point of discrimination, it starts to want to hunt something to attach to. You remember that bit? This point of discrimination is the center of this rolling sphere, if you like. Now, the dimensions of this imaginary sphere are determined by the risk assessment, the LPL of the risk assessment that you did previously. But you can see that, these are the upward leaders and the point of discrimination. And this is the sphere that we're going to roll in a minute. I just wanted to give you this kind of sense of scale. This is a 9 meter to eaves building, which is 30 foot, something like that. Has a diameter of 400 feet. Its actual radius, pure radius, is 60 meters, 197 feet. Class 3, 45 meters radius. Class 2, 30. Class 1, which is the most onerous and it's the smallest sphere, is 20 meters radius, 40 meters diameter. So we then roll this sphere, this imaginary sphere, around the structure or building surface that you're going to want, that you're interested in protecting. Where the sphere touches, so here and here, and if you rolled it that way, then like I say, that red vulnerable point, this is where you need to deploy your measures, your shielding, because this is what theoretically it's saying that the attachment can take place, and that the void, lightning protection zone 0B, if you want to get really technical, is this void here is less vulnerable and therefore considered protected, and you don't need to put any measures in this place, because it theoretically, on this, using this concept, it thinks that because lightning is a competitive event, it's much more likely to latch onto here or here. Does that make sense? So let's see the concept at work, and I'll set this rolling. So as the name suggests, once we know the size of the sphere, we roll it across the surface of the building we're interested in. Now, the beauty of rolling sphere method is that it copes with complex geometries. It copes with them really well, which is why it makes it the most technically secure and robust method of protection that we can use. So you can see now you've got your areas which need some kind of protection installed. Little CCTV camera here included, and we can look at protecting those in more detail. Now, this video made it look easy, but trust me when I say, if you're trying to do the rolling sphere method in 2D, you will be CADing out arcs and circles galore for days and days and days. It takes ages to do it because you have to consider how that ball rolls in 3 dimensions. And this method is very similar to the Ericsson method, which is also supported by the software tool that we're going to look at in a minute, XGS Lab Shield. So why rolling sphere over angles or curves? Well, as mentioned previously, the rolling sphere method handles complex geometries really well. The angle method is a simplification. I don't intend to go into it greatly here because, like I say, we can run courses on this for like 4 days at a time. But if you're interested in technically secure, robust protection designs, then it's rolling sphere, the EGM method, that you really need to look at to get the job done properly. Just to say, I've mentioned a couple of tools here already. At Grey Matters, we use this risk assessment software tool called Den Support. It's really, there are others available. We're not promoting this in any kind of way. The other tool that we're going to use, and we're going to dig deeper now, is XGS Lab's Shield. So let's move on to this bit. So, okay, so for the next 10 minutes, we're going to take a look at one of the major tools that we use a lot of the heavy lifting for us. It's XGS Lab, and this is kind of the welcome screen. So let's have a look at a recent project real quick. And before I do, I'm going to give you a little bit of context here. So this is an LNG storage tank. It's about 50 meters diameter, 50 meters tall to the eave, and probably another, I don't know, it looks like about another 8 or so to the apex. And the bund is about 62 meters diameter. So that's what we're looking at. Another interesting thing about this is that there is an 8x component to it. So you've got a zone 2 covering the purge vents, and then there's a gas, there's a volume of gas that surrounds the tank, which we have to be mindful of and take account of. So although it's a pretty straightforward structure geometrically, it's got its complications. So the first thing we do before starting anything else is to CAD up in 3D the actual tank in a wireframe format. Now you can use any version of CAD that you want: SolidWorks, Revit, AutoCAD. I've got TurboCAD in front of me because it's actually quite a cost-efficient option. So once we've got our wireframe in 3D, we can then import it into the XGS. But before we do, so we've just showing you that that's what's been readied. Today we're looking at Shield, and what we do, we actually follow the top ribbon from left to right in sequence. So you would normally, put the name, what you're looking at, the project name, the customer designer site, if that's relevant. I won't go into that bit here. It's pretty straightforward. So from the project, we then choose our standard. Today it's IEC 62305, and then we'd click on the import option here and steer it to the TurboCAD version and the DXF version of it, and click import. Now, to cut down on time, it does only take a couple of minutes, but just to cut down on time, this is one I prepared earlier. And then we can go to the draw and the layout. So this is a layout. This is a plan view of that tank. There's steel trestle, that's supporting the pipe work, and front elevation and a side elevation to the left there. So that's your orientation. We can then work down the left hand side across these tabs here. So if you were going to add some more components to there, that maybe there's a lighting mast or something, then you could drop in vertical conductor to represent that. But what I would say is XGS has limited CAD ability. It's not a CAD tool. So what I would encourage you to do is to do as much CAD as you can in the specialist CAD package, and then export that into DXF and import the DXF file into XGS. Because the XGS, it's where its value is actually in the computational side of things. That's where it does the heavy lifting for you. So that said, we can look at adding some stuff if you need to, and then just as a sense check, you can kind of view things in 3D as you want, and zoom in, pan around, whatever, the usual kind of controls. And then so now we move on to the shielding parameters, and we've chosen RSM, which is rolling sphere method, and we're referencing the shielding. That's what we're interested in. Next variable is to do with your Ericsson IEEE, so we can ignore that in this case. There is a calculation that it does for you for the Ericsson method, so it's very user intuitive and helpful. And then the S value is the rolling sphere radius in meters, and because you can see that this tank's fairly sizable, In actual fact, this is in Northern Europe. You've got a class 1 has been determined in the lightning risk assessment. So knowing it's a lightning protection level 1 means that the rolling sphere radius is needs to have a 20-meter radius, which is why that's there. Half a meter, that seems fair. You'll see what the results are based on half a meter, and you'll see it's fine for this application. So we go to the results. We've got a choice here of 2D and 3D and this XGL. 2D, if I click that, it generates the calculation pretty quickly. We can see immediately over here, it gives the result not protected. Let's just work that into a 3D view a second. So it's given the 3D as a mesh kind of view, and you can see that the tank itself has got protection blanket over it, but the gas volume outside, the zone 1 and zone 2 are vulnerable. So we could get lightning entering that volume. And as we know from previous, if you've got something that's 30,000 Kelvin, it's going to be a pretty significant source of ignition, and that we don't want. So in this case, it's just showing the vulnerability and it's not protected. We can look at this in more of a rendered view. Let's just change the background to a little bit, get rid of the axes. They're just a bit of a distraction. Let's move that over there and go in. It's, like I say, you can change the way the representation is presented as much as you want. You've got even the colors of the actual blanket. I like this lawn green because it's quite contrasty. And then you can set it in motion. You can actually see in real time where the gaps are in your protection. So in this case, we can see that the tank and the bund, yeah, fine, looking good, but the gas volume surrounding it is vulnerable. So that's a quick representation, and we can sort of move it into whatever plane we want to see it in that's going to help us understand what's going on. So what else can we do? And we can choose like fixed views if we want to. So knowing we've got some gaps in our protection solution, should we call it, we can perhaps work up a different kind of strategy here. And going back to our layout, what we've got here is, we can introduce some catenary wires. Can you see the sag of the catenary wires? There's a really useful tool in here where you can calculate, helps you calculate what the catenary sag would be to enable you to get these realistic things. This is taking from the power of the earthing versions, where you might be modeling an overhead line of 400-500 meters, and you need to understand what the sag is to represent for perhaps you've got an electromagnetic field study that you're doing. So we're migrating that capability across to the lightning protection side of things. So this is just to show you that you can use catenary wires, air rods, whatever it happens to be. So we can check out to see whether this will work. So let's have a look. If we go to 2D view, and well, success. We've got a protected volume now. We can see it in side elevation and front elevation. It all looks good, and we've got a green, nothing poking out of this greenness. So that would indicate to me that everything's good. But let's have a look on the 3D view and see whether that is the case. We've got our lovely lime green blanket. And let's maybe increase the transparency, I think, probably. There we go. And let's pitch that up a little bit. In fact, why not? Let's have a look at this in side view a second. So we can see from this side view that everything is kind of, let's stop that there, come back a bit. We can see that the valves in the trestle structure is protected. We've got some finials that are coming up, air rods, as you might call them, coming out of the to protect that area. We've got the purge vents protected here. Everything looks good. I'm not saying that this is the ideal solution, but it is a solution to making sure that lightning is less likely. It's going to mitigate that risk of entering in and attaching into that volume of gas, which could be explosive at that particular moment in time. What else can we do? We can change the color of the blanket, the protective blanket. I call it a blanket, but that's because it looks like one. So the beauty, okay, reiterating, going back to what we learned in previous slides, the beauty of the rolling sphere method and EGM under IEEE is that it can handle complex shapes, complex geometries, complex sites. So let's have a look at a more complicated geometry here. What does this one look like? Whoa, okay. So what we've got here is an AD plant, AD anaerobic digestion plant. So we've got something over here, which is the methane collection bubble. And you've got some digestive tanks, processing plant, some CHP, combined heat and power units here, and a stack over here. Let's have a look and see what this looks like. So I'll go into results. So let's take that to light grey. So again, it's a pretty rudimentary wireframe model that you're looking at, but you can see now that you can actually model the entire site and the interaction of each structure with one another. So not just, for example, we've just looked at the that tank, that LNG tank in isolation, but you can actually look at the tank and all its surrounding neighbours, if you like, just to see what's happening. And this is what's happening here. Let's change that to lime. Does that help? Probably not. Ah, there we go. Dark green. Okay, who'd have thought it? But we can see now how the interplay of stacks, lighting columns, the CHP unit, we can start to deploy the measures, which is the shielding measures, in an intelligent way to give us the protection blanket that we need. And this is also, this particular site has also got these, we've represented them again as like these little umbrellas, and those are the ATEX zones. There's no need to model complete spheres because that would be computationally quite heavy. So if you thin those down, that's another useful technique to keep the computation time down. So for example, this structure to here, it's not actually a structure, this is a fan, a blowing fan that pressurizes the membrane on this tank, and it has a gas zone around it. So there's no point modeling a complete sphere. So to keep the computation load economic, we only need to put in, fairly scant representations of the gas volumes, enough so that you can see where the protection is and where it's not. So let's have a look at a side view, for example. So you can see just these gas volumes above the tanks themselves. They're quite high up. So hopefully in this last 10 minutes, we've given you a feel for what is possible and the tools that we're using today to take some of the heavy lifting and make our lives a little easier in terms of time, so that we're not spending inordinate amount of time CADing things up when we've got tools like this that can do the heavy lifting for you. So we can work in a productive way. Okay, I think that is all from me. I'm going to open it up now to the floor. If you have any questions at all, please, let's get them out in the open.
Okay, so there's a couple or quite a few that have come in, and that I'd like to pick up on straight away. One is, what about side flash? Does the software kind of consider that? Yes, it does. The principles of the rolling sphere means that, if you get a structure that's really tall, plus 50 meters, then it will show where the structure itself is likely to see an attachment on a side, as a side strike. So then you'd put coronary tapes around, if it's a stack, for example, at suitable intervals up the stack to kind of mitigate that from happening. Okay, another one. So I'm hoping that kind of addresses that question about the side flash. Yes, it does cater for it. Another one is, how is the detailed report by the software? What does it look like, the output? So on the screen that you're seeing at the moment, let me just, what you've seen is the rotational render of the model. To be able to get that into a kind of report, you can do like a screen capture on video, but there are option buttons which will capture will screen grab whatever you pointed at and allow you to then copy it in and paste it into your report. Now, unlike an earthing study, there isn't kind of a predefined template that XGS will follow. So you need to have that kind of document already pre-prepared, if you like, in Word or whatever word processing document you're using, and then you just simply basically copy and paste the screen grabs, the snippets that it saves, and paste them and populate accordingly. So a little bit different to a grounding kind of study, but it still has some neat kind of features to make life a little easier. Okay, a big one here, which is quite specific, which is, can the presenter explain how the lightning protection system can be designed using XGS Lab for a small 138 kV outdoor sub having freestanding masts? Okay, that's quite specific, and I think the team at Easy Power would be really, if you have that outdoor sub, if you save it into a DXF format file, it should only take sort of 10 minutes to run through, just a quick demo to show you, how easy it can be to generate the model, and then potentially deploy your freestanding mast around to protect the buzz bars, to make sure that the lightning attachment doesn't enter into those zones. and provide you with the clearance necessary to provide the protection for the sub.
And I'm just going to jump in just one little extra comment there. The software does actually incorporate IEEE 998 for calculating the sphere size according to your insulation levels. So that way you can calculate what that sphere size is and develop your protection.
Absolutely, David. I think that's, this is where your knowledge of the IEEE, I'm more familiar with the IEC version. So, like I said, the guys from Easy Power will be able to, support you on that very quickly. Okay, what else have we got? Libraries. So when building your model, it's a great question because when building a model, we all like the libraries that we can dip into and kind of pull those items that we might have already had pre-stored to try and be a little bit more productive on building the model. So as I said during the slides, XGS is not a CAD tool. Its strength, if you like, is in the computation side once the CAD model has been drawn up and created. So I would tend to use your specialist CAD packages first and build the layers, libraries in the tool that you happen to be using. So if it's an AutoCAD, then you can build up some blocks, arrays and things like that that you can have stored, and build the model in that first, convert it to a DXF file once you're happy with it, and you're going to try and see if that solution works, and then import it into into XGS Lab, and then run the computation within XGS Lab. So do pretty much all the CAD you can do in the tool that's designed for CAD, then import into the tool that's going to give you the insight and the knowledge built in this case, XGS Shield, if that makes sense. Okay, what other questions have we got? Okay, will the software cycle between UL9 NFPA 780 and UL 96A? I think that's probably one for David. It'll certainly cycle between IEC and IEEE.
Yeah, so that NFPA 780 and UL 96A, those do point to the rolling sphere method as a way to develop your protection system.
Okay.
And that's, again, you can use a standard approach and develop a system, or you can do a more robust approach like this rolling sphere method to confirm that your lightning protection system actually accomplishes those goals. So I think NFPA 780 has some general guidance on the spacing of your lightning protection and things like that. But yeah.
Yeah. Oh, cool. Okay. Okay. Can I see the IEEE comparison slide again? Fixed angle and mesh. Okay. Yeah. Okay. So the question is, can I see the IEEE and IEC comparison slide again? I think because it's pre-recorded, it's going to be a bit of a challenge, but I'm sure that Jim will be able to get that to you, so you can see the comparison slide. In terms, so if you look, so you're looking at IEEE covers the curves, fixed angles, and the EGM, the geometric modeling. The comparison with IEC is that there is the addition of mesh protection, which is like the Faraday cage, basically, and it's a legacy kind of form of protection. You've got angle of protection, which is your fixed angles. The IEC does not have curves. It doesn't use that as its methodology, but the most robust and technically secure is the rolling sphere, which is the equivalent of the EGM in IEEE. But I'm sure we can get that slide to you after the webinar, if it helps. So, are there any other questions? Can I see? Okay, so with regards to the rolling sphere, when modeling, are all 4 sphere sizes used to create the model? Great question. And no, so cast your mind back to the process. Process is you do the risk assessment first. That's the very first step in the overall process, and we do that to get the lightning protection level established. So the LPL. And there are 4 levels of LPL. And against each LPL, so there's class 1, class 2, class 3, class 4, against each one of those LPL, there is a corresponding radius of the rolling sphere. So once you've established a single lightning protection level, you apply that rolling sphere to the structure that you're interested in. Now, it gets complicated when you've got larger sites, for example, and you may be processing like a hazardous area that's got a very high, high hazard, high risk processing part of the site, and maybe there's an administration block that's some distance away. What you don't want to do is to be able to is to apply the most onerous risk right the way across, risk assessment right the way across the site when the admin block, for argument's sake, is relatively low risk. Perhaps it's single story, not very many people involved occupied. So in that case, you might want to divide up and chunk down your site into discrete areas or volumes and treat each one with differently, if you like. So yeah, great question. Okay, so can this be used for HV substations where the sphere radius is based on the bus bar height? And Bill, can you export? Yep. Yeah, great. that answers that one.
Yeah, that goes back to the 998 reference.
Okay, gotcha. Yep. And can you export the DXF from importing? Yeah. So once you've got your kind of model nailed or your solution nailed, what you want to be able to do is then basically export that potentially out back into your CAD software to make some layouts and elevations and things like that. So yes, you can do that. It will export out in DXF. Okay, so it's cost too long, but sure. Do we have a library ready for equipment we can use? I think we've answered that one with the library of equipment we can use. No, but you can create one in your CAD package that you're using. Okay. Are there any more? Oh, by the way, thank you very much for sticking with me on this. It's much appreciated. Hopefully you found it interesting.
Ian, you did a great job. We really appreciate the contribution. And just so the audience knows, we will have an associated Q&A response posted on the website when we put the video up on the EasyPower website for viewing. You did a great job. Thank you very much. And thank you all for joining us today.
Excellent. I shall go and have my supper now.
Thanks for staying late with us, Ian.
No worries.
So long.
Cheers, guys. Bye-bye.
Cheers.